we'll try to look at what I could. See, in this particular slide, I want to draw your attention to this particular number. 10 to the power of 17 watt per centimeter square. This is the intensity of the laser which you would need. But this is just a beginning. Actually, this kind of a stabilization can also happen at low frequencies. But that's a matter of, we'll come to that in the future. Now, you don't have to worry about this pulse duration. I'm not going to talk about a laser pulse. What I'm going to talk about today is a continuous wave laser. Now, the thing is, now we've understood what is the physics behind it. Now we need certain machinery. So, what we need to do is to solve Schrodinger equation for n electrons. And the difference is so far. You don't have a nuclear electron attraction term in Schrodinger equation anymore. Instead of that, you have that smeared out potential, which looks like a diatomic molecule. In the case of an atom pair. So all you have to do is, you can use, see, all of you would have done some amount of quantum chemistry or so forth. You would have used some common packages like games, Gaussian, so on and so forth, which would calculate electronic energies of molecules. Now, the thing is, you can choose any of these. You have to just modify it so that the potential gets replaced by this particular potential, which is the stabilizing potential. Once you have that, you have the machinery to calculate your wave function. You have the machinery to calculate the energies, so on and so forth from this. And you are free to use any method. So, you have the machinery, you know what is the physics. Now, what do you expect? So, just for a handmade calculation, a very simple calculation would be to look what happens when you do a one-dimensional solution for this particular potential. Now, it's just like solving for particle in a box, but you will have to do it numerically. Once you do it, you will see that the wave function gets localized. The ground state wave function probably gets localized in both these levels. It gets split into two. But you could also have excited states which have a major configuration in the middle, so on and so forth. Here, the bottom red one is a ground state. Then I have an excited state. I have not plotted the actual wave function. What I have plotted here are the probability densities. So, now in terms of chemistry, a free field hydrogen atom, the ground state is a 1s orbital, right? It's spherically symmetric. Now, the potential which you have is no longer Coulombic. It's double well, cylindrically symmetric. Even the symmetry is broken. So, what would happen here? Chemistry-wise, what would you expect to happen? Like, what happens when two atoms come together to form a bond? When a diatomic molecule is formed, in terms of valence bond theory, see, here I have a laser whose polarization direction is the z direction. So what you would expect is, you would have a mixing between the s and the pz states, and you would have a kind of s-pz hybridization. So in terms of chemistry, you could have a laser-induced hybridization for the stabilized state. So you can have something like a diatomic bond. That is the message of this. So now that we have an anticipation of what is going to happen, let's really look at what kind of a picture do we get. Like if we are able to look at the electron densities of a laser-dressed helium atom, how it would look like. Now, this is the picture which we get.
You are hinting, but in the higher angular momentum component, the right symmetry will also come in.
That's my point. Actually, the higher angular momentum things would not be mixed much by a laser. The Py and Pz states.
Not Py and P, talking about the dz square.
Yeah, dz square, so on and so forth. This is just if you just consider two pz states. Just even the higher angular momentum things will contribute very much, in fact, just because of the nature of the potential, so on. I had just put this so that we get a feel of it, what would happen. In fact, without doing a calculation, if you think in terms of what we have learned in school and so on and so forth. So, if you do an actual calculation for helium atom at a quiver distance of alpha 0 equal to 5 at units, this is the picture which you would get. Now, it still looks very much like a ground state helium atom. Like, if you were to look at the electron density of a ground state helium atom, the picture that you would get is just this particular peak, just the single peak in position, but much higher than this, much more pronounced. But in this particular, for the case of a laser-dressed helium atom, what you have is, you have these two slight peaks at the points in the double well, right? Just a second. Yeah. See, at these particular points, you have two small peaks coming. And this is because the helium atom gets polarized in the laser, the potential that we have used is different. If you were to go to very large quiver distances, say 50 atom qubits, then what would happen is this middle peak would actually disappear. Now, I'll come to another picture later. So, what if you have a lot of electrons? Now, sulfur atom, if you would make an approximation to it, it's got 16 electrons, right? 16 is the nuclear charge. So then the potential which the electrons would see is a split of 8 and 8 at two different quiver distances, right? Now, the first thing what we have compared here is the electronic energies. We have looked at the electronic energies of O2 molecule, of oxygen molecule, and we have looked at the laser as sulfur atom. They look qualitatively similar to a certain amount of distance, but at the same time, this is without the nuclear repulsion. The nuclear repulsion has not been counted. It's only the electronic energies. Okay? So, now that apart, how does the electron density look like? Now here is something very interesting, in the sense that if you would compare the helium atom and sulfur atom, you would see that the middle peak is completely disappeared. And the two peaks where the wells of the potential are, you would see pronounced peaks. That means most of the electrons are occupying both of those split wells. Now, if the electrons occupy those split wells, what does it mean? The electron has to actually travel a longer distance, right? Now, once the electron has to travel a longer distance, naturally the energy goes up, the internal frequency motion of the electron becomes less, and the stabilization happens. So, this splitting of the wave function is actually a measure of that stabilization. That peak in the middle disappears. If it completely disappears, you have two well separated things, and you have a stable source.
What electrons are we talking in? Because in helium and in sulfur.
Helium, you have two electrons, right? That's one. That's an atom. That's the atom in the laser.
Okay, and the sulfur?
16.
All the electrons we are talking.
All the electrons. All the electrons. In fact, if you would integrate this particular charge density over all space, you would get the number 60. All the electrons. No, none of the electrons have escaped from this system. It's an idealistic. I'm talking about a physical picture right now. So, how could this be realized in an experiment, so on and so forth? We'll come to that towards the end of the talk. Yeah.
So, does both the wells have to be symmetric? I mean, can one be less?
They have to be symmetric. They have to be exactly symmetric.
And how would that be?
Pardon?
The reason?
Because of the general symmetry of the system. The electron density has to exhibit the whole symmetry of the molecule, right?
So, when case of sulfur, you mean there will be 8 electrons in one well and
there would be exactly 8 electrons to the half region of it. And if this particular peak disappears, it would be good to say that all the 8 electrons would occupy this well. That is when the small peak disappears. But otherwise, strictly speaking, if you integrate it in half the volume, you would have 8 electrons.
And if we take some odd, the atoms with an odd number of electrons, then?
Atoms with odd number of electrons, see, then, yeah, that's an interesting question because still you would see half this side and half that side. You would see half this side and half that side.
What about the extent?
No, see, the electrons, what I'm doing is I'm splitting the charge density by half and then I'm integrating half of the charge density there, right? So actually, see, it could be half. There is a symmetric plane, right? There's a mirror plane right in the middle.
Actually, we are calculating the probability density kind of.
Yes, this is the probability density kind of thing. I have not plotted the wave function, but if you were to plot the wave functions, you would see different kinds of symmetries. But here, when I talk about the localization of electrons, I am talking in terms of the electron density, which would be a picture which you would get experimentally. If you would find ways to measure it experimentally.
Just I have a question. When this situation arises,
Yes.
then is it okay to call the helium to be in a singlet S state, or should I call it as a singlet sigma state?
Singlet sigma state.
Because there is no
Yeah,
longer
that is one thing which I wanted to say here. In fact, the 1s2 is no longer a 1s2. It's better to call it a singlet.
Like what I mean.
Yes. Exactly like for a diatomic molecule. That would be the better notation, but again, that would be a better notation. But in that case, symmetry is defined with respect to nuclear positions. In this particular case, symmetry should be defined with respect to a potential, to the potential. In fact, there is also probably, if you were to take a Fourier transformation of the position space wave function and you go into momentum space, then actually there would be always an extra inversion symmetry in the system. So you don't have a C1 point loop in it. This is just usual, if you take usual position space without any laser. So in that case also you have a symmetry enhancement. So right now we have a very vivid picture, not a simple picture of how an atom in a laser looks like. Now the next thing is about detecting these particular states. Now here what I'll do is I'll try to talk about something called a linear Stark effect. Now this is a textbook thing which you have. This Stark effect was found by Johannes Stark. He got a Nobel Prize for it. Whenever I used to present this in Israel, they always used to remind me that Johannes Stark was a Nazi. But apart from that, I think the science which he did was very good. Now, so here what I have plotted is the degenerate states. You have an electric field. Here you have a hydrogen atom. There is no laser, and you have an electric field. So what happens today? You have quite a lot of degenerate states, right? One of the examples which you would take are the 2s and 2p states of hydrogen atom. They are degenerate. Now, once you apply a very small electric field, there would be a mixing of these states, and you would have a splitting of the energy. And usually, in the case of hydrogen atom, it is linear. But in the case of free field ground state atoms, which don't have a permanent dipole moment, there is a quadratic Stark. So the thing is, these are the energies for sulfur atom as a function of the varying laser pattern. What I have plotted here are what I want you to look at is the blue curve. Now the blue curve is the difference between the first excited state and the ground state. Now what you can see here is that at particular values of the quiver distance, rather the laser parameter, this goes to 0. So the ground state of sulfur atom becomes degenerate. Now at this part, now when does this happen? This happens when the wave function completely splits into two. So at this particular point, for a laser hydrogen atom, sulfur atom, if you apply a very small electric field, very minute electric field, you will have a mixing of degenerate states, and then you will have a linear Stark. Now what happens here is, why do these degeneracies happen? Now what I told you is that you have a laser along the z direction, right? So the mixing happens only between the s and the pz orbitals. So you have an spz orbital. The px and py remain fairly unchanged. So as you keep increasing the laser parameter, this keeps going up in energy, or this keeps getting stabilized. While these remain unchanged, they remain where they are. So you are always bound to get a crossing. Since the fast changing SPZ states, they will cross the slow changing PY, PX states, so on and so on. So one of the ways to do it, to detect the dichotomy, rather the splitting of the wave function into two, would be to apply a very small electric field. And here I have plotted the degenerate ground state of sulfur atom, the wave functions rather. And once you apply an electric field, if you take the linear combination of these two, they would split into non-symmetric wave functions. So once you apply an electric field, you will have a linear Stark because of the dipole moment which is present for these orbitals. So that's one way of detecting whether this onset of stabilization has started or whether the wave function is filtered. So till now what we have done is we have talked about atoms. And naturally what a chemist wants to do is to talk about molecules. And this is where we do real chemistry, right? So I'll try to draw your attention to a paper which came in September 2000. This is about helium dimer. There's no laser here, it's just a free field dimer. Now what they have done is, they have done something called diffraction grating experiments. Now I do not know the details of the experiment, but I'll try to read out to you what they have written here. They have said that they have found a single vibrational bound state for helium dimer, and with a binding energy of this, which amounts to about 10 to the power of minus 7 eV. I do not know how they could detect this, but these energy, I don't take these energies numbers as sacrosanct. The thing is, you had a single vibrational bound state. That is, you have a potential energy surface which is very excited, and you have just one level below the threshold, and you just have one vibrational bound state. So this particular vibrational bound state was detected experimentally is what the paper says. And they had also reported a bond length of 52 angstrom, a very, very large extended van der Waals. You can hardly call it to be bound, it's almost separated. But, so the question that we ask now is, suppose you take helium dimer in a laser in a stabilized state, what would happen? In fact, you could think of it, if you take two helium atoms and you confine them to be in a particular volume, that's exactly what the laser does.